you all very much. I am from Olin College. I have one slide about that. This is a new engineering college. It's just outside Boston, 15 years old, and our mission is to fix engineering education. And one of the ways that we're trying to do that is to make engineering as fun as it should have been all along. And my contribution to this, the thing I'm working on most recently, is signal processing using Python. FFT is, of course, a big part of this fast Fourier transform. It is the coolest thing I know. It is useful for everything. The algorithm itself is such an elegant piece of mathematics, and it explains a lot about the world around us. But non-engineers typically don't know about it, and for engineers, it's typically in the engineering program, but in a really painful way. So, I mean, this is a good book in DSP, but if you look at this, you're into chapter 9 before you get to the fast Fourier transform. You're a couple of hundred pages in, and you had a really long slog through mathematics to get there. It doesn't have to be that way. There are a lot of ways to make this really fun. So one of them is by using sound, and one of them is by using Python. The natural reason to use sound is that what's going on in our ears is a lot like spectral analysis. The Fourier transform is doing something that's like human hearing. If you have not seen this video from Vi Hart that's called What's Up with Noises, it's a really nice explanation of what sound is and how human sound perception works. So check out that video, but not on my time. The other part of this, so sound is part of what makes it fun, and Python is the other part. You don't have to slog through all the mathematics before you get to try stuff out. You can do things in an interactive way. This is a link. If you're following my slides, there's a link there to an article I wrote that was just kind of fun. I went to a performance of a grade school band, and I decided to synthesize the unique sound of a bunch of 10-year-olds playing wind instruments. And it's the kind of thing that I want my students to do, is just explore the world using fun tools. This is all a work in progress. I've got a book called Think DSP. It's under a free license at think-dsp.com. So if you're interested, check that out. I'm working on it, so definitely would love to hear suggestions and contributions. Try it out, play with it. The framework that's in the book is thinkdsp.py, and these are the basic objects that make it up. The idea is that a signal is just a mathematical entity that represents something that varies in time, and you can discretize that. So I'm doing everything in discrete world. You can discretize that. I'm going to call that a wave. And I'm kind of abusing the vocabulary just a little bit, but I'm calling a wave a discrete version of a signal. Once you've got a wave, you can go back and forth between the time domain and the frequency domain. So when you take the FFT of a wave, you get its spectrum. If you break a wave up into a bunch of little pieces and take an FFT of the pieces, you get a spectrogram. And you can go back and forth. So that's what the framework looks like. And now, if you're following along at home, you should load up this link, tinyURL, SciPy 15, DSP. This is on NB Viewer, and I'm just going to run through a couple of demos that I use in my class and give you a sense of what it's all like. So the first example there, I'm just going to load up a cosine signal. Again, that's just a mathematical thing, so that's defined for all time. And it's 440 hertz, which is A4. That's tuning concert C. I'm then going to make a plot so you can see what the waveform looks like, and it's a sinusoid. It's a cosine. And make wave is now discrete. And now that it's discrete, you can play it, so we can hear what that sounds like. It sounds like a sine wave. And if you've got perfect pitch, you instantly recognize that as concert A. Now you can make a spectrum of that, and if you're familiar with spectral analysis, you probably know that the spectrum of a sine wave is just a single frequency component at 440 hertz, which is right there. And now instantly, you've played with a couple of classes in Python, but you get a general idea of what spectral analysis is about. You can go one step farther and create a sawtooth. So this is at the same frequency, but it's a different waveform, and so it sounds different. Not a very pleasant sound. And there's what its spectrum looks like. So for me, chapter 3, I think, or maybe 2, is about harmonic structure. It's the sound of a lot of things, speech and music, and many of the things that we hear in the world have a natural harmonic structure like this with a fundamental frequency at 440, and that's the pitch that we perceive, but there are also other components at multiples of that frequency that determine what the timbre of that sound, in musical terms, the sound, what the sound sounds like. The other fun part of this is that any digitized music or sound anywhere in the world, the students can grab this stuff on day one and start playing around with it. Freesound.org is this amazing resource with all kinds of little sound samples that you can grab. And so I grabbed this little performance of a violin that I think is an amateur violin player. And you can make a spectrogram of that lets you see how the frequency components that make up that sound are varying over time. And here you can almost read the melodic line of the music. This one's not visualized particularly well. I didn't work very hard to make it pretty, but you can. And in fact, one of the things that you can do with this, do you know who knows about parson coding? Do you know about this? Oh, this is a very cool thing. So if you have a piece of music like this and you just figure out whether the sound goes up, down, or stays the same, you can encode a melody using U for up, D for down, and R for remains the same. You can then type in that parson code to, I think I have the link here, and it'll tell you what the song is. So I didn't recognize that melody, but I used the spectrogram to figure out the parson code, typed it in, and identified that piece of music. So kind of cool. Just a couple more examples of things that this library does. If you want to pull just a segment out of a sound sample, you can. And so here's just a spectrum of part of that, the violin. And if you pull out the dominant peak, or actually the fundamental peak, it is at 438.3 hertz, which is just a very slightly flat A4. If you are a trained musician, you would hear that that is a little flat. You can pull out the peaks in order to identify that. Yes, here, and there's the parson code. And then you can go look that up, and you will discover that that is, oh, there it is. Okay, I haven't actually looked it up. So I will leave that to you. So go to that webpage, type in that parson code, and you will find out what that song is. Everything so far has been perfectly periodic, but most sounds vary in time. So I've got a chirp here, and here's a function that generates a sawtooth chirp. So the waveform is a sawtooth, but the frequency is increasing linearly over time. And if you look at it as a sine wave, or rather as a waveform, it just looks like a sawtooth. You can't quite tell that those are getting closer and closer together, but they are. Here's the spectrogram. And you can see that the fundamental tone is increasing and all of the harmonics are increasing, and the harmonics bounce off the ceiling. Yeah, you can kind of see that there. It's a little hard to see, but the harmonics bounce off the ceiling because of aliasing. So when the harmonic exceeds the Nyquist limit, it aliases down and sounds like it's at a lower frequency. Now, what do you think this sounds like? I'll give you a hint. You will recognize this when you hear it. That's the red alert signal from Star Trek, the good Star Trek. Because that's what you need when you're dealing with an emergency, is something in the background going. Everybody stay calm. All right, I want to do one more demo. How many of you know about LTI system theory? Linear time invariant systems? Okay, if you don't, that's all right. The idea here is that you can characterize a channel, a communication channel, by sending an impulse through it. And if you know the impulse response, then you know everything you need to know about that channel, and you can figure out how that channel would respond to any other given input. Now, one of the ways to put an impulse into a sound system like a room is to fire a gunshot. And again, my friends at freesound.org do things like record gunshots. And that is what that sounds like. So now that you've heard the impulse response, you know everything there is to know about the room acoustically. sort of. I'm really simplifying things, but. And so now you can take that, I think this is the same wave, right? This is the original. So now if we convolve the violin with the impulse response, what we're going to get is a simulation of what that violin would have sounded like if it was played in the room where the gun was fired. And here's what that sounds like. It kind of sounds like a violin being played in a firing range. Which is exactly what it is. So those are some of the demos. This is the fun stuff that you can do if you take a computational approach to DSP using Python. So just to wrap up, let's see. I've talked about synthesizing basic waveforms, the fundamental idea of going back and forth between the time domain and the frequency domain, and a little bit about filtering. The central idea of the whole thing is this idea that when you have things that vary in time, there are two ways to look at the same function. And I like this figure because it shows in 2 dimensions the time domain and the frequency domain. The rest of the book, I mentioned chirps. We do noise, so there are lots of different kinds of noise. You can both generate different kinds and also characterize noise. Autocorrelation is kind of a cool topic that's not usually in a DSP class, but it turns out is very useful for pitch tracking. Anybody play Rock Band? You can sing into the microphone and it tracks your pitch, and I always assumed they were doing Fourier transform, but I had a chance to talk to one of the engineers from Harmonics, and he said, nope, they're doing just brute force autocorrelation. So that was kind of cool. I do discrete cosine transform, both because it has applications for compression. So MP3 and Ogg Vorbis are all based on cosine transform compression. And it's a perfect stepping stone to the Fourier transform. So this is where the students finally see the mathematics of it. Discrete cosine transform, everything is real valued. So your head doesn't explode thinking about complex numbers, and then you just take one more little step. The transform is exactly the same, except complex signals instead of real signals. I mentioned filtering, I mentioned convolution, and LTI systems. That's the outline. We did the chirp demo. We did the convolution demo. All of the code for both the book and everything that you just saw is all in this GitHub repo. And again, I'm kind of early into this project and would love collaborators to send me corrections, add new material, whatever you want to do with it. So again, signal processing is great. I don't want to belabor this point, but it really, most double E's will see this material, most mechanical engineers, but I really think all engineers should get this. All scientists should get this. Anybody who's going to be looking at time series data should know about signal processing ideas. So I would love to see this get out of engineering and be adopted more widely. I think Python is a tool that can make that happen. Pretty picture of a spectrogram, and lots of ways to get in touch with me, and also my slides. If you didn't grab them at the beginning, you can grab them now. Questions? Yes, sir.